Okay, we're looking at question 9 now from 0654, winter 2017, paper 4-1. Alright, we've got our snowboarder and we've been presented with a speed time graph. Okay, it's always a good idea to just have a look at these graphs, even though there's no question directly associated with it yet. It's a good idea, for example, to note that the maximum speed up here is 5 meters per second. Also quite a good idea when you look at this data to think what kind of things could they be asking me. It's a speed time graph. It might be asking about acceleration, they might be asking me about speed, about distance. Okay, let's have a look. Okay, we're told that the mass of the snowboarder, and I've circled it and I've written the label M there to allow myself to sort of ease that cognitive difficulty. I know the thing there, I don't need to hold it in my brain. I'm being asked to calculate the kinetic energy. Kinetic energy is one of those ones that we very rarely use the triangle for. However, you could always do it, it's just a bit awkward. Kinetic energy half mv squared. Okay, now we're being asked to find the maximum, which is key. Well, if you've got maximum, i.e. EK max, yeah, then that is going to come from something changing here, okay, from the maximum, one of our variables. Well, mass wouldn't change during this process, however, we've just seen that V does change, and the maximum value of V is 5. So we're doing a half times the mass, 75, times the maximum speed squared, it's 5 squared, 937.5 joules. I would always take that to 3 significant figures, 938. I think even in the mark scheme they do to 2. That's okay, don't worry about it. Okay. We're asked then to calculate the acceleration of the snowboarder in the first 10 seconds. Okay. Key obviously for you to go back then to your graph, find 10 seconds, which is down here. Yeah. Follow up. Okay, draw on the graph. Graphs are made to draw on, and we're getting to 4 meters per second there, not the 5. Okay. If you use 5 here, then the time you'd have to use there is 12, and I don't think you would get the marks there. I'm not entirely sure. Sorry, 12.5. Come back. Okay. We're calculating our acceleration. Remember, acceleration on a speed time graph is just represented by the gradient. Yeah, acceleration is the gradient. That's what we're calculating here. We're calculating the change in y, the change in x. Here, y is speed and x is time. We've got 4 and u equal to 0 because we began at speed equal to 0, and we're getting 4 take away 0, which is 0.4. Notice in this one, slightly different, 3 marks. The reason that there's 3 marks here is for the fact that you've got to include your units, and your units are meters per second squared. Another way of writing this is meters square seconds to the power of -2. Both are fine. I should have mentioned, by the way, in this first section up here, that there's another 3 marks here. The 3 marks really are for identifying that value of, the third mark, sorry, is really for identifying that value of Vmax. So not just using the equation, but being able to identify it from the graph. All right, last bit. We said we calculate acceleration. If you calculate acceleration, you are almost always going to have to calculate some kind of force. We're asked to calculate the force required to produce the acceleration. Force is mass times acceleration, F equal to ma. You have calculated the acceleration up here. You've got a mass way back at the beginning of the question, so now it's just a nice simple calculation. 75 times 0.4 equals 30 newtons. Now obviously there's an issue here that we're using a value that we have calculated in a previous thing, in a previous question. The principle generally is error carried forward, right? So what that means is that if you calculated this one wrong, okay, I was actually about to calculate it wrong because I misread the graph slightly the first time I did it, caught myself though. If I did this wrong, I would then obviously be using the wrong value of acceleration. Well, obviously my force would be wrong. If I did everything correctly and I just used the wrong value, then I'd still actually get 2 marks here. You've got to be aware of that when you're marking your own papers. Don't just look at the mark scheme, think about it a little bit. If you used your value, you got 0.3, you're obviously not going to get 30 newtons. That's fine as long as you did the working correctly. Okay. Quite a lot in this question. Snowboarder is then exposed to infrared and ultraviolet radiation. How many times have we seen this in our paper 4.1? Okay, we want to place the radiations infrared and ultraviolet in their correct positions. Okay, and again, I urge you to try and remember this in whatever way you can, that really the link here is visible light. Visible light sits in the middle of my electromagnetic spectrum, but in visible light, as you've seen in the dispersion experiment where we split white light out, we get violet at one end and red at the other end. Why is that important? Well, we want to know where infrared is. Infrared is next to red. Ultraviolet is next to violet. All right? And again, we've done this a few times. Up here, this is our gamma. This is high frequency. And so down here is low frequency. Up here is low wavelength. Up here is high wavelength. So you may be asked to explain the trends that we're having here. Here we're increasing the wavelength, but decreasing the frequency. Here, if we're going to the left, we're increasing the frequency, but decreasing the wavelength. Why is that the case? Well, because we've got this equation V equal to F lambda, and we know that V is constant. Now, really important, again, we've seen this already, but the kicker here comes in the fact that they've decided this time to use kilometers per second and not meters per second. Okay, I think most of us are all right with the idea 3 times 10 to the 8 meters per second. Well, if we're doing in kilometers per second, we need to divide that by 1,000, which brings us down to 3 times 10 to the 5. Now, unfortunately, if you wrote 3 times 10 to the 8 here, you would lose a mark. That's quite brutal. It's just a case of reading the question very carefully. So, whenever you're doing this, check units. That's one way of tripping you up. The reason for this, doesn't matter what value you put in, is because our ultraviolet is an electromagnetic wave, EM, okay, and all electromagnetic waves travel at the same speed in a vacuum, all right? And that's why we have this behavior that I've just mentioned about F and the wavelength, right? V is equal to F lambda, that's our wave equation, it holds for all waves, all right? But we are saying that for EM, V is the same. It's always 3 times 10 to the 5 kilometers per second. Why is that important then? Look, if F goes up, lambda must go down. If lambda goes down, if F goes down, lambda must go up. That's where this relationship comes from, okay? The fact that electromagnetic waves travel with the same speed means that the frequencies and wavelength are inversely proportional to one another. Okay, let's look at question C. Again, I think I've seen another similar one, this idea of latent heat. Latent effusion is not a hard concept for you guys to get, but it's not on the syllabus anymore. Don't need to worry about using that. We're looking at the temperature, yeah, and you should see the temperature is under 0, it's because it's in that solid state. Gets up to 0, we're melting, increasing temperature, and then we're boiling. Yeah. Explain why the temperature of the snow does not increase in section X. You could just ignore this last bit and we could still try and get 2 marks out of this question. Okay, because the first thing really what you have to do is identify what is happening in section X. And I've just said that is melting. Okay, it's a change of state, which means the temperature is consistent or constant during that time. A bit confusing for some people because you assume that if you're heating something, then the temperature goes up. Well, we know that whenever you are heating something, you are putting energy in, and that energy must go somewhere. Well, if it's not making an increase in the temperature, what it's doing is separating the molecules. Okay, so that energy is still going in, it's just not causing temperature change. Okay, that's something I still think you guys could do quite without knowing this term, latent heat effusion. The energy, by the way, is called the latent heat effusion. Latent means hidden, and so it's kind of as if it's hiding because there's no temperature rise. Okay, and that's all for our question 9.